Hello, everyone, and welcome to my lab. Are you ready to learn? Are you ready to have some fun? I want you to pay close attention to everything that's going to be happening. I don't want anyone to miss out on the excitement that we have when we do science experiments. We do them safely. I want you to look and see that I'm wearing my eye protection. I'm wearing my goggles, and I want you to see that I have a fire extinguisher right here, ready to be used, just in case something goes out of control. We're not planning on anything going out of control, but we have it as a safety precaution. You and I know where it is. I'm going to set it on the side here. It will be used if it is necessary to use. My next experiment is with carbon dioxide. Carbon dioxide, of course, is a greenhouse gas. We know that. Carbon dioxide is also in all carbonated beverages. But I'm going to use carbon dioxide not as a gas, but in a solid form. And it's called dry ice. So I'm going to put my gloves on to protect my hands from frostbite. I don't want my skin to be damaged. I pick up a chunk of dry ice and put it right here. The temperature of dry ice is minus 78 degrees Celsius. It's really, really cold. And dry ice changes from being a solid to a gas directly without melting by a process we call sublimation. Can you say sublimation? Sublimation. Sublimation is happening right now, but we can't see it. Why can't we see it? Because carbon dioxide gas is mixing with air, which is a mixture of gases as well. So I ask you to focus your attention on what you see between my two hands right here. You see glass cylinders. There's 6 of them, and they have liquids in them. How do we know they're liquids? We just shake them up a little bit. We know from experience what liquids do when they're shaken. And they're arranged in pairs according to the color of the liquid in each cylinder. So this pair has what color? This one. This one. Let me ask you if you think this helps improve seeing the colors. Does this help? All right, I'll put it there. So now I'm going to take chunks of dry ice and put them in the cylinders, and you'll see that I'm putting the dry ice in every other cylinder. Is anything happening? Do you see any bubbles? What kind of bubbles are those? They're carbon dioxide bubbles. They're coming from the sublimation reaction. But we see them now because gas is mixing with liquid. You also see color changes. Those color changes tell us that a chemical reaction has taken place. And the colors are there because of dyes we put in there, and these dyes change color when the pH of the liquid changes. So carbon dioxide dissolved in water gives us carbonic acid, and all the colors to begin with were colors when the liquids had a base in them. So we have acid-base indicators, and the color change indicates to us that a reaction has taken place. All right, so let me ask you a question. In this pair here, where I put the dry ice, the color changed from what to what? How about in this pair? Pink to what? Clear. This is a clear and colored liquid. This is a clear and colored liquid. This is clear and colorless. From now on, no one who comes to my lab will confuse the words clear and colorless. They don't mean the same thing, right? So let's now focus on what's coming off the top here. It looks like smoke, but it's not smoke. You know what it is? It's really a mist. It's condensed water vapor. It's a fog. It's the same thing as the stuff that floats up in the sky. What's the name of that white stuff floats up in the clouds? It's condensed water vapor. In this case, the water vapor is condensing on the carbon dioxide gas that's coming from the sublimation reaction, and we see this effect here. So let me put a couple of more chunks of dry ice here because I like the bubbling as much as you like bubbling. Do you like the bubbling? All right, so there we go. So now I'm going to take this bucket of dry ice and move over here where I have a dishpan. It's empty except for air. And I have some water It is boiling. You see the water bubbles coming off there? I'm going to use my gloves now to protect my hands from heat. I'll take this flask, it's full of boiling water, and empty it into the dish pan. What do you see coming off the top? Steam is invisible. You cannot see steam. You're seeing condensed water vapor. And the mist dissipates when the temperature of the hot water vapor gets to be the same as the temperature in the atmosphere. So now I'm going to take the bucket of dry ice and dump it all the way in here. I'm still here. This is how they make fog in the movies sometimes. They take boiling water, add dry ice to it, and they make fog. And you notice that the fog is moving downward, telling us that carbon dioxide gas is denser or heavier than air. And it makes all the nice bubbly sound that we see over here. You like this experiment? Yeah. I have several people doing research in my lab, and at this time I would like you to meet one of them. Would you please welcome Juliana? Hi, Juliana.
Hi, Bassam.
What do you have for us here?
I have been working with the solutions in these flasks.
Yes. And what do the solutions do?
Well,
or what do you do with the solutions?
I will show you. Look.
Nice.
So I had to shake it very, very strong.
Yes.
Now look what happens when I give it a little swirl.
Ah. What's in those flasks, Juliana?
This one has a solution mixed with water, glucose, and potassium hydroxide.
This first one?
Yes.
Okay.
And it also has a blue dye called methylene blue.
I see. So water, potassium hydroxide, glucose, and methylene blue.
Yes. This one has the same exact thing, but with a dye called rosacerin.
Rosacerin. Well, but what happened to the colors?
Well, they're fading.
Yes, I can see that. Can you regenerate the colors?
I think so. Why don't you give it a try?
Oh, you want me to do it?
Yeah.
All right.
Why not?
All right. Shake harder?
Yes.
Like this?
Yes.
All right. How about this one?
I think you can just
do this?
Yep.
How about if I shake hard?
I think it happens the same. But
now,
look.
Yeah, will the colors fade now?
But not as fast.
Well, what do we have to do?
Just wait.
Just wait. Be patient.
Yes.
Whenever we do scientific experiments, we have to be patient. Whenever we do anything worth doing in life, we have to pay attention and be patient, right? And look at that. The colors are fading.
Yes.
So color changes give us an indication that there is a chemical reaction taking place. And you told us what the ingredients are.
Yes.
So, Juliana, I know you have a lot of other interests in addition to working in my lab.
Yes.
Like what?
Well, I am a musician and I play the bassoon.
You play the bassoon?
Yes.
Do you have it with you here?
Yes. Let me look for it. Oh.
All right.
Oh. Well, I only found the harness. Like, wait a second.
All right.
I have to wear this because it's very heavy.
Uh-huh. And you don't need your goggles anymore.
No, I don't, because I'm not going to be working with experiments. Hold on. So here's the bassoon. Did you know it? Yes? So this is a woodwind instrument. So it's made out of? Yes, exactly. So you see that it has a lot of shiny little keys. They are coated with silver. And what they do is that when I press them, they cover and open some holes so that the air goes through and makes the notes work. So when I play it, they just make the sound work. So I'm going to try and play something for you so you can hear it. Something's not working. I think I forgot something. Oh, there it is. So it looks like I need this little reed to make it work. It sounds on its own. That's the best thing. Look. So you see, that's what actually makes the sound in the bassoon. Different.
Juliana, would you please play something for us?
Yes, of course, but I would like to invite my friend Ross to join me.
That would be great.
Ross. We will be playing a duet from Giacomo Rossini, from one of his operas, The Barber of Seville.
Thank you very much, Ross, and thank you, Juliana. Wasn't that beautiful? And now I'm going to do an experiment using this device that has a light bulb up here and 2 electrodes. It's plugged into the electric outlet, but I want to show you that the 2 electrodes are not touching each other. If I complete the circuit by using this metallic surface, you'll see that the light bulb comes on, okay? So anything that helps to complete the circuit will make the light come on. So I have 2 beakers that have a clear and colorless liquid in them. Actually, the liquid is water, and then 2 beakers that are empty except for air. So let's see whether water conducts the electric current. I don't see any glow. Do you see any glow? The second beaker also has water in it, and you see nothing glows. What I'm going to do is take some table salt, add the table salt in there. It dissolves, and I stir it up a little bit. Not all of it has dissolved. Now let's see what happens. we learned that table salt solution conducts the electric current. So it has ions in it that are charged particles that carry the electric current across. All right, so before I do the next experiment, I don't want to contaminate anything, so I'm going to rinse the electrodes right here, and I'm going to use a household chemical. You can see what it is. What is it? Vinegar. So I put the vinegar in this beaker, about that much, and now let's see what happens when I test the vinegar. I see a faint glow. Can we turn the lights down, please, so everyone can see that there's a faint glow? Even darker, if you can, please. Thank you. So, vinegar, with the lights back up, please. Vinegar is a weak conductor of the electric current. So with the lights up, please. Yes, thank you. And before I check the next household chemical that I have, I'm going to rinse the electrodes. The next one is, you can see what the next one is, right? What's the next one here? This one. All right, so I'm going to set the electrode right here, and I'm going to take the household ammonia, put in as much as I put in of the vinegar, and let's see what happens. Once again, there's a very light glow. Would the lights down, please? Now you can see the very, very weak glow, telling us that household ammonia is also a weak conductor of the electric current. Would the lights up, please? Because now what I want to do is take the vinegar and mix it with the ammonia, the household ammonia. So I'll keep the electrodes in there. Are you watching this very carefully? And I mix them like this. And I get a very strong conductor of the electric current. That tells us that when vinegar combines with household ammonia, we get ions. And these ions carry a lot of ions, and these ions help conduct the electric current. So, all right. Did you like that experiment? Yeah. For my next experiment, I'm going to use this large glass beaker sitting on this platform. Inside the beaker, which has a volume of 4 liters, there's a magnet coated with Teflon. And I'm going to turn the motor on and turn the light on. And I need to mix 3 things together. I only have 2 here. Where's the third one? I don't see it here. Could someone please bring out the third liquid that I need? Hello, Bucky. Good to see you, Bucky. Bucky is a very good chemistry student. You see Bucky is wearing goggles, obeys the safety rules. And Bucky, I like that you have your Science is Fun button on there, so I know that you like science too. All right, Bucky, let's do the experiment. Let me do the experiment here. I'm going to add the first liquid. Here's the first liquid, clear and colorless. All right, you got your goggles on. I'm going to add the second one. Not anything much exciting happened. This is a volume increase, okay? How about you add your third liquid there, Bucky? Let's see what happens. All right, you ready? All right, add it. Just put it in, Bucky, like you've done before. All the way. Wow. Bucky, look at that. A beautiful blue color that we see right there. And now it's yellow. Back to blue. You think it's going to change again, Bucky? We just wait a little bit and see, right? There it goes again. Bucky, you like this one, Bucky, right? Yeah. Would you like me to tell the audience what's in there? Okay, so we have water, we have hydrogen peroxide, we have malonic acid, sulfuric acid, potassium iodide, manganese sulfate, potato starch is in there. The yellow color that you see now is the color of iodine. It combines with the potato starch. We get this beautiful dark blue color, which is characteristic of having iodine with starch. And the oscillations continue. This is a chemical oscillating reaction. And Bucky, this is one of my very favorite chemical reactions. Bucky, I know that final exams are coming up and you have to go study, but let me ask you before you leave, Bucky. How long is it going to take you to graduate? 4 years? Yeah. You are going to graduate. That's why you came to UW, right? 1, 2, 3, 4. Lift up, let me see. Lift up. 4. It's going to take you 4 years. 4 years. Everyone should aim to finish in 4 years. All right. Bucky, I wish you the best on your final exams. Thank you so much for coming by here. Thank you, Bucky. Thank you, Bucky. Now I'm going to do an experiment where I use this beaker that has in it a clear and colorless liquid. It's water. And this other beaker, the same size, but is empty except for air. I'm going to take some food coloring, add the food coloring to the water, and ask you to watch and see how the green color diffuses and mixes with the water. That's beautiful patterns. Of course, I want them to be mixed very homogeneously, so I'm going to stir it up like this, all right? So we have this nice green color. And what I'm going to do next is take some powder. Actually, I have a small amount of this powder right here. I'm going to take this powder and put it in this beaker. And I need to put actually a little more. So I'll scoop out some more. More is better, right? Not always. Sometimes it's just more, right? So put that in there. Put that in there. Now, I want you to help me as I do this experiment. I'm going to take the green liquid. I'm going to add it to this beaker that has the powder in it. I'm going to count, and you help me count, see how many times I can go back and forth, all right? You ready? Here we go. You can't count beyond 1, is that it? No. You see that this powder is a superabsorbent of water. It has absorbed many times its volume in the liquid. Some of you might know about practical applications for this powder. You're nodding your head, yes, yes. Yes, it's used where? In diapers. It's used in diapers. It also has other uses too. It's a superabsorbent of water. And if I add a little bit of table salt to this gel that has formed here, let's see, add the table salt at the top, and then I take the glass rod and I mix the table salt with the green gel. You can see that the table salt, which has a lot of ions in it, when it's in solution, it is breaking up the gel features of the experiment that I did. Let's see if I mix it all the way to the bottom. Let's see if I can reach the bottom here. And now, can I pour the liquid back here? Yes, now I can pour. You want to start counting again? No. I didn't put salt all the way down here. So this is an experiment that shows properties of different materials that have a lot of practical applications, a lot of practical uses. For my next experiment, I'm going to use a very long spiral glass assembly that's connected to a funnel at the top, and at the bottom there's a large beaker. There's the funnel, spiral glass assembly, and a beaker, and I'm going to mix 2 liquids, a clear and colorless liquid with a clear and colored liquid. And I'm going to do the mixing in the dark. So can we have the lights down, please? All the way down. There you go. This is the release of energy in the form of light, but not in the form of heat. This is the phenomenon we call chemiluminescence. Chemiluminescence is related to bioluminescence, and most of us know about bioluminescence because we know about the firefly reaction. You've been a great audience helping celebrate this very special anniversary, and I want you all to remember, no matter what you do, as you do the experiments carefully, to be paying attention to what goes on, and to also remember science is fun. Thank you all very much. Thank you. Thank you. Come on out. Come on out.